So it's a pleasure and an honor to introduce today's speaker, Alexei Davydov, from the University of Ohio, who'll be speaking to us about tensor categories and the Bogomolov multiplier. Yeah, well, we're very few, but if at any point anyone wishes to ask a question or make a comment, please go ahead and unmute yourself. We would also like to have a questions round at the end of the talk. So yeah, thank you very much, Alexei, for accepting our invitation. Please take it away.
It's a pleasure. Thank you for inviting me. Yeah, I will be a bit ambitious today, trying to squeeze maybe too much, but let's see how it works. As I imagine, it's a category theory seminar, so things like tensor categories really don't need to be defined. But yeah, I will flash through definitions. If you want me to slow down, just let me know. Again, any questions at any time are most welcome. So the Bogomolov multiplier seems to be of interest more and more from different points of view. Yeah, I didn't know that it really first appeared in topology, but I'm an algebraist, simple-minded one. So for me, the easiest way it appears is really in the question when a twisted group algebra, a twisted by two cycle is isomorphic as an algebra to a group algebra, and then yeah, the answer is homology classes of those cycles have to be in what is called the Schur multiplier. I'm using a slightly different notation for it. I stripped it from the subscript 0 because there's only one b in the story. There's no b1, so why to carry it along? For me, the interest in my interest in the Bogomolov multiplier comes from symmetries of tensor categories, especially modular tensor categories. And modular tensor categories really appeared first in theoretical physics in rational conformal field theory. So my ambition is to reach that. And Bogomolov multipliers, so these two cycles with this property that restriction to any abelian subgroup makes them trivial, is behind the sort of exotic property of corresponding invariance of conformal field theories. So the conformal field theories will be coming from the Albi-Hall construction. I won't have time to explain what is that, but at least algebraically, I hope I will be able to just give an indication of how it happens. So first tensor categories, but I will just put it all on the page, and notation. Notation is the only reason I'm putting it. Yeah, we have tensor product on the category, and tensor usually assumes that it is linear. So tensor product is bilinear, and yeah, most of the time my categories will be semi-simple. So there's no nothing special, just direct sums of simple objects. Categories are effectively categories of vector spaces or their sort of Cartesian sums. The tensor product, what makes them interesting. Tensor products can be quite bizarre in a sense. It is far from usual tensor product of vector spaces we are accustomed. And the usual category story is whatever equations we have in ordinary algebra, like associativity equation for a product, when it categorifies to level of categories, then equations become isomorphisms, and then we have syzygies, so high equations coming from interesting ways of composing these isomorphisms. And the perfect example is this MacLane's or pentagon axiom for the associativity. We can arrange associativities which work on the triple tensor product. If we take a quadruple tensor product, we can arrange them in the form of this pentagon, and the usual ask is to for that pentagon to compute for any possible x, y, z, w. So the example which will be of interest is the category of vector spaces, but with a flavor. So we take a finite group. We can take any group really, but finite is better. So take a finite group and then consider the gradients on the vector spaces by this group. So that is just direct sum decompositions of a vector space into summands which are labeled by group elements. And then the tensor product, we could make it compatible with this group gradient in the following way. So if we just take two graded vector spaces and tensor them, we define the degree G component to be the product of all possible components where the degrees multiply into that given G. So that is usual, really that is a kind of a cryptic formula for the usual degree property. The degree of the tensor product is equal to the product of degrees computed in the group G. Kind of usually graded vector spaces are graded by the cyclic, infinite cyclic group, but here are all finite groups are allowed. The tensor functors, again, the general definition. The same story when we categorify, we have to replace equations by isomorphisms and then bring in higher coherences. So the equation we replace by this isomorphism is that of a homomorphism. So a map F between two things where we can multiply the homomorphism when this map is compatible with the products. But now compatibility is a collection of isomorphisms, a natural collection, and then high compatibility is this diagram. Again, there's no ambiguity. It's the only thing we can build out of associativities we have in the source and the target of this functor F and the tensor structure of the functor. And that is to commute for all possible x, y, and z. Yeah, I will be suppressing when the diagrams become too large. I will be suppressing the tensor sign, but it's reconstructible. So an example related to the previous graded vector space categories is the change of gradient along a homomorphism. And that is just a sort of covariant functor procedure. So the I promised to look at symmetries at autoequivalences of categories, and the special will be this softness. And this is a categorical phenomenon. We can see it in usual algebra, and that appears because in categories, because we have now more freedom. We have two layers, level of objects and level of morphisms. And soft for me is something which is sort of trivial on the level of objects, but interesting on level of morphisms. So that's a general slogan behind it on. And trivial on the level of objects is just being as a functor, as a plane functor, not a tensor functor, being just identity. But on the level of this coherence, rather, of this tensor structure, it is to be interesting. So that is the informal meaning of soft tensor autoequivalence. And notations again. So the group of isomorphism, tensor isomorphism classes of such symmetries will be this for all of them, and then soft things compose into soft to form a subgroup, and that will be the sort of main object of investigation for me. And in easy characterization of this, so that is a normal subgroup, and because it is a kernel of the homomorphism which computes the effect of an autoequivalence on the Grothendieck degree. My categories, as promised, will be all the time semi-simple, and so the condition that something that the functor autoequivalence F is identity as a functor is the same as the condition that its effect on the Grothendieck is trivial. So that's why we have this alternative characterization of the subgroup of soft autoequivalences. And we could now look at the category of graded vector spaces and already have interesting examples, but they're kind of trivial. So if we take the identity functor as the functor for the tensor equivalence, we still have a freedom of defining. Let me go back and illustrate how that was really the reason for this diagram. So you can have still the freedom of choosing this coherence isomorphisms. And because it's identity functor before and after, so let me go back one more slide. This is identity, this identity. So we really have collection of automorphisms of tensor products of two objects, natural in each of those objects. And if this X and Y are graded vector spaces, so we have a freedom of introducing some scalars in each of the graded components. So I'm sorry, I'm going to run back again and give the answer. So here's the answer, and the scalars are they depend on the degrees in which we take our vectors U and V from. But when we fix the degrees, then they're just scalar operators, and then the condition, the coherence condition. I'm sorry, I'm going back again. I hated myself, but I don't know any better way. So this coherence condition will be nothing but the two-cycle condition. The associativities are not interesting here. The associativities are just the trivial associativity of the tensor product of vector spaces. That works well for graded vector spaces, but these are interesting. So this tensor structures of the functor F are interesting. That's what we define using the function on the group Cartesian square way. And then if you look what happens in these two compositions, you will have two sides of the two-cycle equation. So going forward again, sorry, close your eyes. So that's why I'm assuming that gamma is a two-cycle. And yeah, so the isomorphism classes will be coboundary. So homology classes of these two cycles. It's easy to see that two functors F gamma and F gamma prime are isomorphic as tensor functors if and only if there is a coboundary between gamma and gamma prime. And then the group of isomorphism classes of these solved symmetries is the second cohomology. And the whole group of symmetries is not much bigger. It's just extended by the symmetries coming from the symmetries of the group. So that is really when we don't take the identity functor, but we take some other functor, but it has to change graded components to graded components as wholes. And that procedure has to be group automorphism. It has to.
Can I ask a question?
Sure.
So tensor here is isomorphism classes. Is that correct in the notation here?
Yeah.
Now,
so
if we
this is isomorphism class. Yeah.
So if we actually look at this, I guess if we don't take isomorphism classes, this wants to be a two group. Is that right?
Yeah. So that will be categorical group. Yeah. And then and that will be the pi naught with whatever you call it. And then the pi one will be easy. So pi one will be just H1. H1, okay. Sorry. Yeah, H1 cross the center, I think. H1 crosses. No, yes. No, just H1. I'm sorry. Just H1.
Okay.
So yeah.
And then would pi 2 be the cocycles themselves?
No. If we're talking about homotopy groups, then there will be these small things. But yeah, you could sort of you could represent this categorical group as a so it's a categorical group. You could represent it as a cross module, and you could choose for that cross module to be yeah, so again, it's a freedom. You work up to equivalence. So you could take the cross module, which is the semi-direct product of Z2 with automorphism groups, and then that is one component of the cross product, and the other component is Z1, and the cross product homomorphism is just the differential. So that will be almost a billion, but yeah, up to this semi-direct product in degree 1.
Sure.
And yeah, still very simple categorical group. Thank you for the question. Yeah. Of course, categorical groups are much better than just homotopy groups of them. But in this case, it will be falling apart into two homotopy groups, so there will be no Postnikov invariant between them. Right. Okay. Just because of the effective abelian sort of origin of it. So I will also have my real question will be about symmetries of braid things. I'll have to remind you of what is braiding, but yeah, it's just the commutativity categorified. And when we categorize commutativity, something interesting happens. So usually, yeah, people from the beginning of category theory, MacLean and Allenberg, they had commutativity categorified, and it was called symmetric. And it is this collection of natural isomorphisms between x, y, and y, x, satisfying. They didn't write it like that. It's actually interesting, but yeah. So they had, let's say, one of such axioms, and then the condition that the coherence C done twice is identity. So that's what happens when we look at vector spaces. This C thing can be just the swap of vectors, decomposable vectors. And then, if you do it twice, of course, you have the identity. And then you just need one of the hexagon diagrams. But if you don't assume that that this braiding is involutive, that the square of it is identity, you still have an interesting story. It's actually more interesting story. And that was a relatively recent discovery in mathematics and algebra. That was, of course, Royal and Street. The paper they published really in the beginning of 90s, but the preprint they had was from early 80s. About the same time, maybe slightly later, physicists came to the same structure, studying Russian conformal field theories, and it's really strange. So that is for me a true quantum phenomenon coming from category theory. You don't have this ramification of commutativities in ordinary algebra, but the more category levels you have, the more interesting versions of commutativity you have. That is, of course, in topology, well known from mid of last century. These are the EN spaces. Yeah, the interesting thing is that MacLean, in his book, he just screwed up one of these diagrams, or maybe two. His definition of braid is incorrect. Be aware. Which is strange because Allenberg-MacLean's sort of cosmology is effectively all about that. This is a low-dimension example of Allenberg-MacLean cosmology computation. Okay, so the symmetries will be of braided categories, and they will have to be compatible with the braiding. But this time, it's not a structure; it's just a condition that the tensor structure of the functor is compatible with the braiding before and after the functor. So when we will talk about autoequivalences, it will be sort of the symmetry condition on the tensor structure, that this and that are sort of the same in a way. And again, new notation. So the autoequivalences, isomorphism classes of them, which are compatible with the braiding, will be represented by the subscript. And the first, more or less interesting example are these braided autoequivalences of the category of representations of a group, linear representations, complex numbers as a coefficient. The first fact which I need to recall is that all braided autoequivalences of such category are just coming from group automorphisms. But this time, some automorphisms become trivial on their corresponding factors become isomorphic. Namely, when we have conjugation with a group element, then this group element can be used to construct an isomorphism between the conjugation, autoequivalence, and the identity. So the resulting group of isomorphism classes is just the outer isomorphism classes, and the explicit form of those is just the change of action along this automorphism. So the other thing, which is I think even easier, so that is the fact which you could prove in a different way, but people usually refer to sort of the big gun of Berlin's theorem, which says that these categories are so-called Tanakian, and they have a canonical fiber factor to the vector spaces, which is in this presentation just a forgetful factor. But the canonical is the important bit, and then any symmetry preserves this canonical thing, and that's why really any symmetry comes from the symmetry of the group. The next fact is really classical, easy one. It's just the fact that the Grothendieck, the character ring of the group, is a lattice in the space of class functions. That is 19th century end of it. And then if we're interested in soft things, I mentioned before that they can be seen by at the level of the Grothendieck rings as doing nothing there. So we are ending up with the automorphisms which preserve conjugacy classes, all of them. So automorphisms which are moving elements, but not changing conjugacy classes. Of course, inner automorphisms are such, but there are examples of non-inner class preserving automorphisms, and this group can be non-trivial. For simple groups, it is trivial, but there are interesting solvable groups where it is non-trivial. And then the first statement is that the group of soft braided autoequivalences of this representation category is just this group of outer class preserving automorphisms. So now I'm getting to the main object. This calling it Greenfield double. Usually double referred to Hopf algebra behind the category, but I'm using the name. I'm calling the category the Greenfield double, and the category is sort of a mixture of the graded vector spaces and the linear representations. So objects are first of all graded, but then there is an action of the group. The compatibility is this. So if you take something of degree G and act with a group element F, then the degree changes to the conjugate of G with F. And the morphisms are just gradient and action preserving morphisms. So this is really the answer to the question. Yeah, the tensor product is just the graded vector space tensor product, but we have to extend the action from the factors to the tensor product, and that is just the diagonal action. And you could see it all keeps the consistency condition in place. The associativity is just the usual associativity of the vector spaces. But the interesting turn is that this now is a braided category. If the group is G is non-abelian, the graded vector spaces were not braided because really the tensor product was non-abelian. But if we look at these sort of graded and acted upon vector spaces, then for them the tensor product will be abelian on the level of Grothendieck rings, but it will be actually commutative on the categorical level. So this is the braided category with this braiding. And again, it's interesting to compute that the degree is preserved and the action is preserved by this map. So these are the maps in the category and morphisms in the category. And then they satisfy hexagon axioms, which really become just triangle axioms with the trivial associativity. So yeah, that is really the answer to a certain computation. Natural way of this category to appear is as the center construction of either vector spaces graded by G or representation category of G. The computation for this center for the graded vector spaces is more natural, is easier. And it's a general fact, again, that this categorical center, monoidal center, or Greenfield center, or Royal Street center is braided, is always braided. And that's really kind of a slightly deeper explanation why this is braided. And yeah, autoequivalences, will be interested in this soft braided autoequivalences of this guy, and it's actually not answered what is the group of isomorphism classes of all or braided for these categories of G. But I will be interested in soft, and they are easier because of this softness. They really preserve any subcategory because the functor, one level functor is just identity, so it doesn't really move objects. And then any subcategory is fixed. So that's why I will be looking at certain subcategory in this category of Z of G, and that will be the category where the gradient is trivial, where all graded components by the trivial, but the trivial are empty, are zero. And then this category is just the category of vector spaces, so these graded components with the action. And the action will be just the ordinary representation, linear representation action. And then I have, I will be interested in the group of symmetries, a group of autoequivalences, braided autoequivalences, which fix this subcategory. So that is possible to describe, and that is easier to describe first. And the first fact, again, coming from some categorical constructions, which are quite general, but I probably shouldn't bother you with them, is that symmetries of the graded vector spaces give rise to all possible symmetries like that. So the actual way they give rise is, as I mentioned, this category is the monoidal center of this category. And so any symmetry, not braided preserving because there's no braiding here, any symmetry gives, promotes to the braided symmetry of this. That's why we have the connection between those. And then this promotion really keeps the subcategory of trivially graded fixed. And then explicitly, when we promote symmetries of VG to the symmetries of ZG, that's what happens. So we can take some group automorphism and then see what it does to these vector spaces. And then it changes the gradient and it changes the action simultaneously in this way. If we take a Tuka cycle, and then first look at the corresponding symmetry of VG and then promote it to the center, to ZG, then that's what will happen. It will only be changing the action. So the gradient will be stable, will be as it is, but the action will be sort of changed by extra factors. And the factors will come from the cycle. And the general symmetry will be just a composition of two such. So then the next step is to do the same as we did with representation category. Just look at the effect let me go back and sort of reproduce the logic. The soft symmetries are is a subgroup in here. And then we know that in general, soft things are those which do not move elements of the Grothendieck degree. And so now the next step is to look at any of the symmetries and see which any of those, and see which are soft. And to do that, we can just look at how what is the effect of this on the Grothendieck degree. So that's why the Grothendieck degree. And as with representations, there is this notion of character, which can help this Grothendieck computation with Grothendieck computations. So the definition is now like that. We have it's a function of two group elements which commute f and g, and the value of the character corresponding to an object on these group elements is just a trace as a character, but the trace of the group element g as an operator on the graded component labeled by f. And that's why we need this commutation condition. Otherwise, it won't be an operator. It will be moving zf into some other z. But if they commute, it will be a linear map from zf to itself, an operator, so we can compute its trace. And then the statement as before, as with representations, that the Grothendieck ring of this Drinfeld double of the center of categorical center of G is the lattice in the vector space of sort of double class functions. Double class function is a function on pairs of commuting group elements, which is stable under joint conjugation.
So and does this generalize to like higher dimensions? If you have like a digraph Witten in higher dimensions, sorry to interrupt, but you know, as you said before that for I guess rep G or vec G, I guess you said rep G, the characters gave a lattice. Well, so the K0 is a lattice in the characters, and now you have the K0 of the center. Are I think these are called bi-characters sometimes. Is that right? Or these are bi?
I'm not sure by double. Yeah, so people call them names, but yeah.
But does this kind of thing? Do you have an intuition for whether this keeps working in like?
Yeah, of course.
Higher, if we keep taking centers, do you get triple character or these?
Yeah, I'm not sure about this side, the categorical center construction, but yeah, the reason. So you mentioned digraph fit and topological field theory, so that is easier to kind of link because this is just coming from the torus. So this is the state space of the torus in topological field theory, two-dimensional torus. And the pi one is z cross z. So you just have homomorphisms from z cross z into G, and that's why this up to conjugation. So that's why this set of double conjugacy classes. Okay. So that promotes to digraph fitting theories to all dimensions, but you would have high-dimensional tori, so you'll have the same story. The state space will be this, and the interpretation in terms of again in what is the this side you say in for three-dimensional torus you have to in the fact that this is the same as a two-dimensional torus state space is because you read the two-dimensional torus as sort of the trace of the identity on the circle. And the circle value is this category, and no, it's not a trace. if you read it as a trace, you will get some other description like endomorphisms of the identity function of this category. But to get the Grothendieck-Green, you have to read it slightly differently. So yeah, that site is less easy, but yeah, you generalize in topology. There's no stopping point.
Yeah,
you just have high dimensional Taurine, and you will have these class functions on the collection of arbitrary lengths of commuting elements. Yeah, good question, but
thanks. Yeah, sorry to interrupt. Yeah.
no, you're fine, because yeah, I think I will have enough time to say everything. So then back to the computation, the effect of these functon characters is given by this formula. So that is a straightforward computation. As soon as we know what is this as a object of set G, we can compute the trace by this formula. So that is all easy, and that's the result. In terms of characters, that is the result. And then again, if you remember where it was coming from, we need those pairs T and gamma for which the effect is trivial. So this side is the same as FZ, the same as this side. And for all objects Z, right? So it's trivial on the Grothendieck-Green as a whole. And instead of, since it is a lattice, we can just take arbitrary class functions and see what is it for phi and gamma to know to move class functions if they're supposed to move them in this way. And yeah, it's easy if you just take delta function on a pair, on a conjugacy class of a commuting pair, you will see that phi has to preserve such conjugacy classes. So it has to be double class preserving phi. And then these coefficients have to be 1. So let's look first at this condition, and I'll call it solved for a Tuka cycle. And the condition literally says that Tuka cycle is symmetric each time we have commuting elements F and G fed into it. It doesn't depend on the order. And it is a cogomology condition. Boundaries are all symmetric, and then we have well-defined quotient. And that's what I claim is the same as is usually defined Bogomolov multiplier. So that's how it appears, coming from the cocycle part of these equivalences. But we still have the automorphism part, and for that to be solved, to give a solved autoequivalence of the category, it has to preserve double conjugacy classes. So it has to work like that. It has to be class preserving, but even more. Still, people, strangely enough, people were interested in such, and they computed, group theorists found non-trivial examples. I was surprised to find them. So there are groups, there are P groups where this is non-trivial and probably unbounded. You can get it as big in size as possible. And then the main fact, the main result, the main theorem is that the total is just a symmetric product of the two types. So coming from the group symmetries of this double class preserving kind, or coming from two cocycles which are symmetric from this Bogomolov multiplier. So that's why I was interested in Bogomolov multiplier from the first. But okay, so this is all kind of categorical computation. Why it has any interest for conformal field theorists? Here is a quick review. So first is a construction. Taking any braided symmetry of a category, we can turn it into a different sort of object. We could use the tensor structure of the factor to equip this with a multiplication, and that becomes an algebra object in sort of a double of the original category. the category is not in the original Greenfield double way, but sort of an external double way. So this box tensor product is the lean tensor product for semi-simple categories is just a tensor product. You take irreducible objects in here and take the Cartesian product with irreducible objects in there, and home spaces you just tensor. So that is the lean construction for semi-simple. And yeah, the sum in this definition is over isomorphism classes of simple objects. Again, no problem with semi-simple G. The bar on the other side of the green product is to represent the change of braiding in the category equipped with the inverse of the original braiding. And yeah, some computation makes it, yeah, gives a commutative structure, commutative algebra structure on that. Again, the origin of this is sort of canonical if you have braided tensor structure on the functor F. So that is a general fact. G can be any braided category, any braided fusion category. But if G is what is called modular, then this algebra is not just an arbitrary commutative algebra, but something which is called Lagrangian algebra. So first, what is modular? By modular, yeah, I mean the braiding being as far from being symmetric as possible, so-called non-degenerate type of braiding, meaning that the things which are transparent with respect to the braiding are just copies of the identity object. So transparent, thinking of topological field theory, you could represent braids as, yeah, it's not topological field theory, really. It's kind of string diagrammatic language inside the category. So if you represent the braiding as a string like that, labeled by objects in the category, then double braiding will be just the, my fingers are too short. So this is a double braiding, and then you could ask when it is just unbraidable, for which pairs of objects. So you could fix one color on one string and then ask for all other strings to pass through and call such special colored strings transparent. And that is the definition of the symmetric center. And then the non-degeneracy of the braiding, the modularity of the category is the condition that there's only one sort of obvious transparent object, which is identity. All other transparent objects are just direct sums of it. And that's what happens for this category Z of G. So in general, monodal centers are non-degenerate. That is proved some time ago by Wilger. And in particular, this Z of G construction is modular. So in this case, this algebra is what is called Lagrangian, which means that it is sort of maximal in a way commutative algebra. The literal definition uses the notion of local modules, so dyslexic modules, according to Paragas. And that is a procedure of, so if you take a commutative algebra in a braided category, and you could still look at modules, even without commutativity, but if your algebra is commutative, you could equip this category of modules with a tensor product, of relative tensor product over your algebra. The interesting categorical phenomenon is that in general, it is not braided. So you're starting with something braided, you're taking the commutative algebra, forming the category of modules, equipping it with a tensor product relative over this algebra, but the tensor product is not necessarily braided itself. So that was discovered by Paragas. You have to really make it sort of more restrictive. You have to take certain modules over which the tensor product, relative tensor product, will be braided. And this special condition on modules is called dyslexia locality. Locality because it really corresponds to the locality of fields in field theory. And if you do that for Lagrangian algebra, then you don't have any modules. So that's being Lagrangian. There are no local modules. So that is the procedure. In general, procedure of taking local modules is sort of like contracting the original braided category. You cannot do it forever because a certain quantity really decreases. The dimension of the category really gets smaller in sort of strong multiplicative sense. And so you cannot do it forever. And the stopping point, yeah, it's called maximal isotropic. But when the stopping point, when you contract, take these local modules and end up with just vector spaces, that's what is called Lagrangian. So there's the categorical algebraic definition, but really the reason of why people are interested in them is coming from conformal field theory. So kind of briefly, from categorical point of view, what is the data of a rational conformal field theory? In terms of category theory, it's just a pair of these modular fusion categories for left and right moving sectors. And then the sort of way it is glued together is by this Lagrangian algebra in the line product of the first and the opposite of the second. And sort of analytically, say in terms of partition functions, that makes sense. So the kind of Grothendieck class of this object set will be the sum of representations of objects from left and right categories. In the conformal field theory story, these categories are really categories of representations of certain vertex separate algebras, of certain chiral algebras. So chiral operator, really the conformal field theory story goes in totally opposite direction. You start with, say, the state space, and that is what sits behind the object Z, this Lagrange algebra Z. And then on this state space, you have the state space correspondence. You have sort of way of composing your operator distributions, and that is encoded in the algebra structure of this object. But then among the operators, you have sort of chiral left and right chiral operators, which are kind of depending holomorphically or anti-holomorphically on the position you insert these operators in. So there's a bit of geometry in there. And that's what gives these two vertex separate algebras. So all the analytic information can be packaged into these vertex separate algebras, and they are rational in the rational case. So the categories of the representations properly defined are modular tensor categories. And then the whole state space is just that object set. So for example, when you take partition function, meaning that you really grade this huge infinite dimensional vector space by conformal weight, then you have a function, generating a function called the partition function, and then it is a sum of finite number of products of characters of this chiral algebra, of representations of this chiral algebras. And that is really the nothing but the sort of decomposition of this object in the Grothendieck. So multiplicities should be 9, should be 0. Multiplicities of this object in a simple basis of these two are these numbers which people call modular invariants of the rational conformal field theory. So the easiest case is called Cardy case. Is when the left and right are the same, non-heterodic is also called, but also the special case for this gluing pattern for the modular invariant. Really, as an object, is just the direct sum of object for all simple objects of object X, and then its dual. So that's a special case when a special construction when the autoequivalence F is identity. And now the final bit linking it with the bringing group G along. We could for that we could start with any sort of holomorphic vector subgrid algebra of central charge a multiple of 24. So the easiest example, Leech lattice vertex algebra, or maybe if you like the monster. But yeah, you could take any other. So there are how many? 90 something such in 24.
Very easy. Yeah.
Yeah. So holomorphic refers to the fact that representation category is just vector spaces, no interesting representations, but just the regular action on itself. And then we could create more representations by taking what's called orbifold on the level of spiral algebras. We just take the product of some number of copies of that V, and then take the invariance under permutation action of some group G. And that will be a sub-vertex separator algebra, sub-chiral algebra, and there we will have interesting representations. So that will be given by the category set of G. That is kind of the rational conformal field theory origin of digraph-Witten three-dimensional theories. And then to construct, so that is just the chiral left or right side. To construct the full rational conformal field theory, we have to glue the two sides using some Lagrangian algebra. And we could take this Lagrangian algebra coming from autoequivalences. And then if it is a soft autoequivalence, on the level of underlying state space, we will just have the same as in the trivial Cardi case, but the operator product expansion, the algebra structure will be different, will be twisted by this soft interesting tensor structure. And so that's how Bogomolov multiplier gives rise to surprising examples of full rational conformal field theories with a Cardi invariant, but not isomorphic to Cardi case. So yeah, I think that's it. Thank you so much.
Yeah, thank you very much, Alexei.
Right.
Yeah.
So as I understand, you are interested in Bogomolov multiplier mostly through its application to topology, right?
Mm. Yes, mainly in the extensions of free group actions. Yeah.
Yeah, that is strange how it pops up in totally different places. It would be interesting to see. Yeah, there should be some connections. Really.
Yeah, somehow. Yeah, my expectation is, the way Carlos and I have been interested in Bogomolov multipliers is actually on the homological side. So there's a homological definition of the Bogomolov multiplier. And just a warning, this is just like the Schur multiplier of a group, right? So you can define it in terms of the cohomology of the group with coefficients in C star.
Yeah.
But you could also define it when it's a finite group, you get the same thing by taking the group homology in dimension 2 with integer coefficients. So these are isomorphic, but there's no natural isomorphism. And there's something similar going on with us, which is for us, the natural side is the homology side. And what I'm wondering is if, I don't expect there to be a natural identity between the Bogomolov multiplier in the cohomological sense and in the homological sense, but it's possible there's a way to build isomorphisms kind of using your interpretation and TQFT ideas, because right, you're somehow identifying, if my understanding of TQFTs is correct, when you get a soft automorphism of the Drinfeld center, that will give you an autoequivalence of a digraph-Witten TQFT that basically acts by the identity on the torus state space. And what I'm wondering is if our understanding of the Bogomolov multiplier, Carlos and I, in the homological sense, could give a way to do this topologically. So to actually build such autoequivalences of the TQFT by kind of doing a surgery or something. And what I have in mind, so the important thing here is to, before I could go further, would be to explain the homological understanding of the Bogomolov multiplier, which is that instead of being a so cohomologically, it's a subgroup of the usual cohomology. Homologically, it's a quotient of the homology with z coefficients. And so what's the quotient? It's take the usual homology with z coefficients and then quotient out by the homology classes that the way we would describe it as topologists is that they're supported on a torus. So, so the homology classes of G, you can think of it as being represented by surfaces mapping into the classifying space of G. And what we do is we kill off all those homology classes that are represented by toruses. So it's only the higher genus surfaces that are somehow contributing to the Bogomolov multiplier homologically. And just somehow one might imagine, how do you build the action, like maybe one could build an action of the homological definition of the Bogomolov multiplier on a digraph-Witten theory, kind of in a way that you've built the cohomological action on the module on the modular category. So I haven't actually figured out how to do that, but maybe it's possible.
But that should be possible by all indications. So topological, depending on the flavor, it's effectively the value on the circle, right? And the circle value is at G. So there's some extra fluff depending on topology on your cobordisms, but it's at most like central charge. But the central charge is still trivial. So that for digraph-Witten theory, it's really just all topological field theory is controlled by these categories at G. So that should be possible. Your expectation, I think, is just totally realizable. It should be a geometric way of interpreting this these autoequivalences.
Yeah, what I'm not sure is if there's a dual somewhere that I'm missing, because I don't know if it's possible. So to take for me, I want to take a homology class. Well, in this Bogomolov quotient, so I have a homology class up to toral classes, and I want to take that. And can I use that to actually build the autoequivalence directly, or is it more like I need to think of that as kind of a what do I like somehow being dual to the cohomological thing? So I'm not sure.
Yeah, that is interesting.
But also, I think it should be really important at which level of TQFT we are talking about. So it's a 0 + 1 + 2 TQFT, or it's a it's two-dimensional. Yeah. 2 + 1. 2 + 1.
Yeah, it's actually this kind which extends to the point. So really, it extends. Digraph-Witten extends to 0 dimension, right? So probably it is
3,
still
2, 1, 0. It's fully extended, I guess.
What? Could you repeat, Eric?
So when I was talking about autoequivalences of the digraph-Witten theory, I meant the 2 + 1 dimensional digraph-Witten theory, but the theory extends all the way down to points. It's a fully extended TQFT.
Okay.
Yeah. So it is so really symmetry should be of the whole thing. I don't think anything changes if we add one. We should definitely add 1, because that's where this autoequivalences operate. They operate on the value on the circle, but it should. Yeah, it extends to the 0 dimensional point.
Also, but this paper of Graham Siegel and Gregory Moore, where they talk about the open closed TQFT side, and also there is instead of talking about the Griffin double, that you are just manage G-graded vector space and also with an action. Could we just reduce to the G-Frobenius algebra? So the objects are G-Frobenius algebra, yeah, and maybe that's another structure, yeah.
Yeah, so if it is just Frobenius, I imagine you're just talking about two-dimensional, two in one-dimensional things. I think that this is too shallow to see the solved thing. That will be just Frobenius algebra, so there will be no second layer where it can be solved. That will in my understanding that will be just ordinary algebra, right? So this Frobenius algebra, you have equations, not equivalences, not isomorphism.
Okay.
So there will be no freedom for solved. You have to add one more dimension. You have to have like 3 to 1 at least, and then you have this. So that it's new to me, but you mentioned that it's very very natural. What is the sort of TFT interpretation of the softness? And it seems like it's something which is trivial in dimension 2 and 3.
Okay. Oh,
but you have to have one where so you have to have 3 layers where you still can have something on tree.
Oh, okay, and there's not a similar result because when we have the representations of a group and also this three-field double, it's like the open part of a closed TQFT, and when you want, when you start from an open part and you want to recover the closed part, you have to you have the open category of difference, and then you take the automorphisms or the natural endomorphisms of the identity functor. So in certain sense, it's like the next level of the autoequivalence. So
yeah,
it is.
I think I see it slightly differently. So maybe okay. So like in two-dimensional case, you would have a commutative Frobenius algebra and not necessarily commutative one for the boundary for the open component, right? So that is more in Siegel. But when you have more layers like 1, 2, 3, then you will have a modular category for the closed sector, and for the open sector you will have just a tensor category, but with a compatibility. So this Cardi compatibility, so this Cardi compatibility is really saying that if you take the open category, which is just a fusion category, and you compute its center, then it will be the closed sector.
Okay.
So really, there are several solutions, several boundary conditions for the fixed open. So you can take Z of G, but yeah, you have two sort of obvious solutions. You could put representations on the boundary, or you could put graded vector spaces on the boundary. But you could have some mixtures depending on the structure, internal structure of G. You could sort of have the full spectrum of mixtures between graded and active on the boundary data. So that is how I see the boundary extension. That is for me, that is sort of a different direction. But yeah, I haven't thought of the symmetries when we have a boundary, because yeah, I was using in the computation that these solved things they fix subcategories. So this if you put representations on the boundary, then it should all be like stable. If you put graded vector spaces, just trying to compute it now. So if you put graded vector spaces, you will only be probably, and you want the symmetries to preserve the boundary extended, you will probably have to lose all the Bogomolov multiplier. Maybe not. Maybe that's what will only survive. Oh no, that's opposite. Yeah. So that will be getting rid of all the group symmetries in the soft autoequivalent group, and we'll be only keeping Bogomolov multiplier. So maybe Bogomolov multiplier is just the universal symmetries, all boundary extensions. Maybe you're right.
Yeah. Oh. And
but yeah, haven't thought about it. Really good question. Thank you.
And also, Alexei, I think when you construct this this conformality theory, really you are not getting a G-equivariant conformality theory. So you are getting an orbifold or version, or
yeah, it's sort of an orbifold, but yeah, it's an orbifold starting from orbifold in chiral sector. So really, it's like if in terms of the state space, you orbifolding by G cross G. So really, it's an orbifold separately working in each chiral sector. It's easier to just do the chiral orbifolds first and then glue them. That way it is kind of more natural. But yeah, it should be possible to describe it as just orbifold theory when you take just a holomorphic and cross itself. And then you still have and you have the only Cardi case possible there. And then you orbifold the still the n tensor power of that. But yeah, maybe not n. I'm confused. No, I wouldn't be able to say it intelligently now, but yeah, it should be possible to do it from the from just full safety point of view.
I could ask another question. I don't want to keep you too late, but I could definitely ask another question.
It's fine.
Too.
No, it's fine. Yeah.
Okay.
It's not too late for me. You see, guys.
Where are you right now?
I'm down under. I'm in Australia. So
okay.
My day is just unrolling. So
you are not in Ohio. Okay.
I'm not in Ohio now. That's why I was asking to shift the time, because
yeah, good point. So so my first question is, so I can think of this center ZG as taking whatever vec G or rep G and equivariantizing. So, but I should properly think of vec G or rep G there as being, well, I guess vec G here as being a G-graded fusion category, or I guess modular category, even a G cross modular category. I think of vec G as that. So if I have some other G cross modular category, and I equivariantize that, so I get some orbifold theory or whatever you want to call it. Do you expect to have a subgroup of the soft autoequivalences of that thing be your subgroup?
That is equivalent to the statement of boundary extension. So really, if you start with some other cross category, it's just that boundary data, and then the Carty condition compatibility with open sector is the center is that G. So you're really picking up some other interesting boundary data, and yeah, just trying to compute it now. My expectation would be that Bogomolov symmetries would still survive for any possible boundary choice. They will still be kind of consistently working, extending onto the this boundary TFT. So probably that's the answer. All which extends to the all possible boundaries will be the Bogomolov. Maybe it is the statement that, yeah, maybe I was wrong saying that we can take the full digraph written extended to dimension 0. Maybe to dimension z, if we extend to dimension 0, that the symmetries will shrink down to just the Bogomolov.
Yeah. Okay.
Yeah. So because of sort of different boundary conditions really forbidding some of the automorphism type of soft autoequivalence. But yes, really right questions.
Cool. I guess
I wasn't seeing them before.
I've kind of had other interests unrelated to Carlos and I, our stuff that kind of got us connected to Bogomolov multipliers, and it was just pretty surprising to see your work on this stuff. So, you know, I really want to understand in a separate project with Colleen Delaney. I think you know Colleen. Maybe so these you know, representations you get of tensor of mapping class groups in the G cross cases, and I guess so. Just a naive question for me would be for I guess for vec G, well, for these digraph Witten theories, is it possible these the soft autoequivalences have a complement inside all of the autoequivalences? Because that would somehow tell me like every autoequivalence is either just a permutation of the it's just like it's an isomorphism of the K theory of the Grothendieck ring, composed with some soft autoequivalence. And I would expect no. The answer is no in general, but it would seem kind of like if that were always true, like every autoequivalence is like the soft in any category, and maybe the soft autoequivalences have a section, you know, or have a complement, so that the total group of equivalences is a semi-direct product. That seems like a lot to hope for, but I don't know of examples off the top of my head that don't have that, and one way or the other, I guess, and because somehow,
I would be surprised if it is. I don't have a concrete example, but yeah, again, it's the right question. So I just realized that I don't know the answer for the whole group of equivalences of that of G.
Yeah, you mentioned that, and that was striking to me. Like I presume people would know that, but it might just depend so much. I guess it depends so much on G.
It depends. It depends on G. So yeah, if G is simple or close to it, the answer is trivial. But if G is on the other side of the spectrum, like nilpotent or solvable, then yeah, it's quite interesting. So it sort of sits on. I know rough answer, but I don't know the group structure. The best I can do is just set theoretic sort of description as a set. But the group structure in this description is somewhat hidden, and
is it because the representation theory of G is so hard? Possibly, is that
that kind of the general answer for inequivalence between ZG and the G prime is sort of easy. The slogan answer is kind of easy. You just need to have a normal abelian subgroup in both the same, and then the quotient groups have to be isomorphic, again the data of an isomorphism, and then some sort of cosmological data on this abelian subgroup. We should be took a cycle on that, which is sort of invariant under the action of the quotient, and there should be some extra compatibility. Sort of precisely you compute the cosmological stabilizer of this supercycle, and that should be the two groups should really sit inside.
Okay. So it sounds like you have like a procedure to figure it out in principle for any group, but somehow it's a mess. Yeah.
It's a cosmological mess, and yeah, it could be probably computed in the concrete examples, as I said, but the group operation is in this data is so unpleasant. So saying a question about complement, right? You couldn't interpret soft in this language, but group operation is such an ugly thing. So seeing that it has a complement always, yeah. But I would be surprised if it does. So it's not an counterexample, but it's an example. Yeah, if we take soft tensor equivalences of great vector spaces, yeah, there is a semi-direct product. There is a splitting. But if we take just say braided out equivalence of representation category of G, Then we have the outer automorphisms of G, that is the full symmetries, and then the soft class preserving. And I don't think there's any splitting in general.
Okay.
That would be surprising if there is. Maybe people just didn't look there. Maybe there is a splitting there, but that would be surprising. I wouldn't expect that. I should look back at examples, concrete examples, but I don't think.
Just naively, one might hope to just somehow reduce like the study of autoequivalences to soft ones, and then like the actions of the Grothendieck ring. But it's probably too much to ask.
So sort of like a splitting, not splitting, lifting a symmetry from the Grothendieck level down to up to the category level. That would be really nice if there is some sort of topological reason for that. But I would be really surprised. It would be really something surprising if it works. If it is possible. So you were mentioning this topological interpretation of Bogomolov as a quotient in homology. Could you give me some references I could sort of study?
Yeah. So I could try to pull it up real quick. It's Primož Moravec.
Moravec.
Is kind of the person who put his finger on this. He's got a paper, I think, in the American Journal of Math. Let's see. This is it. Oops. Put it in the chat there. So there's his preprint. So he just observes, in the case of a finite group, the Bogomolov multiplier is naturally isomorphic to the dual of a homological construction. And that's the one I mentioned. So he does that in the first couple pages. And then he goes and says, well, when you're, I don't know, theorists seem to like cohomology because there's all kinds of tools for like understanding cohomology theoretically. But when it comes to actually computing, like on a computer, I find the homology is much easier. So that's what he was able to do. And having this homological, he could just brute force and find a bunch of examples of things with non-trivial Bogomolov multipliers. So so he goes through this in the first couple of pages there.
Oh, thanks. That is definitely interesting. It was really a nice opportunity to talk to you guys. I hope,
No, thank you very much to you, Alexei.
Thank you very much. I wish I'd understood more, but I'm starting to see why there's a lot of fascinating things going on here.
Bogomolov definitely struck a gold there. This condition is sort of surprisingly just everywhere. and it's non-trivial condition. Examples are really sort of on this nilpotent and. So
there is one quasi-simple group, right? So none of all the simple groups are Bogomolov multipliers are trivial, but there's one quasi-simple group. It's one of the covers of PSL 3.4. There's exactly one that has a non-trivial Bogomolov multiplier.
Oh, that's cool.
Yeah.
Wait for something.
No, it's a pleasure to have you here, Professor Peter. And also
thank you. I was sort of a wire, but it was beautiful watching all the discussion.
We will invite you to all these kinds of sessions. Maybe you, Alexei and Eric, maybe you could send me a possible speaker for that could be related, and we can just still working in these directions. Right now that some possibilities is allowed, maybe it could be. I can include it in this category seminar, and then we can follow with this discussion with another speakers.
Related to Bogomolov, I only kind of again, we probably know guys from Israel. Boris, but so related to this group theoretic tensor categories, I don't think I'm not sure if it's really close to your projects, but so yeah, Dmitry Nikshich, standard co-author.
Maybe next one we can invite to Moravis.
Does Dmitry have papers with Bogomolov multipliers in them?
No. He's
okay.
yeah. That's what I was going to say. He's